Thank you for tuning in. So how many of you have heard of the late Colonel John Boyd? Not many, I suspect, so I'm going to begin with a story. It is the day after the F-15 is turned over to the Air Force. The Pentagon brass is thrilled. The F-15 is a revolutionary fighter, and the generals know it. But Boyd is not happy. He and a small team dubbed the Fighter Mafia assembled to create the lightweight fighter program to build an even better fighter plane. The last step before plane production could begin was to get approval from a committee of three-star generals who were determined to kill the project. But before this meeting, Boyd and his team meet with the Air Force Chief of Staff and the Secretary of Defense and gain their approval not only for the F-16, but also for the new A-10, another plane that the generals don't want. Days later, Boyd goes to the meeting of three-star generals and informs them that the meeting will not be a decision meeting, but an information meeting, as the planes have already been approved. One of the three stars leaving the meeting was overheard saying, "That fucking Boyd." The first combat mission of the F-16 was by the Israeli Air Force. It was the only plane in the Israeli Air Force fleet with the range to strike the nuclear plant that Saddam Hussein was building in Iraq. The mission was a success, and Iraq never became a nuclear power. This certainly helped America's military during both Gulf Wars. The A-10 went on to destroy a majority of the Iraqi tanks in the first Gulf War. The A-10 was the most feared plane by the Iraqis. Not bad for two planes that the generals never wanted. This presentation is part 3 covering Boyd the Inventor. In Boyd's retirement, he wanted to give further scholarship to air combat. Boyd read a wide variety of books on liberal arts including physics, psychology, anatomy, and philosophy. From his readings and endless conversations with numerous subject matter experts came Boyd's paper called Destruction and Creation and his Patterns of Conflict presentation, where the OODA loop was introduced. In its simplest form, represented by the picture on the left, is the wheel of observe, orient, decide, and act, or OODA. A more complicated depiction is on the right. Originally designed for fighter pilots in air combat, Boyd expanded the OODA loop to explain success or failure in most of the major battles in world history. The Blitzkrieg attack of France in 1940 is perhaps a perfect example of OODA applied to armies. Boyd asserts that OODA is essentially the way all humans process their environment. We observe, then orient our observations based on factors such as cultural traditions, previous experience, genetic heritage, and our ability to analyze our observations, then decide on a course of action, and finally act on that decision. We then observe our actions as they impact the environment around us, and the process repeats. Boyd asserted that the pilot who could run through the OODA cycle fastest would win air combat. In this presentation, we will attempt to answer the question, can OODA apply to process automation in the form of operator performance? Let's investigate OODA a little deeper by defining some terms. Observe. This is data collection. The worst possible way to observe is to look up values off of graphics and write them down on an operator log sheet. The best possible way to observe is to have the information sorted and prioritized for the operators via the query display, high-performance HMI graphics, alarm management, and trends. Orient. This is where the observations are analyzed. Training, experience, and aptitude form the basis of the orientation component. A DCS's ability to supply relevant supporting reference information quickly to the operator can also help. Decide. The better the orientation process, the better the decision. Act. Implement the decision. Use of sequences rather than commanding individual devices can quicken the ACT component. The DCS is like bookends of the OODA loop. It should facilitate OODA by providing fast observations and fast actions. The DCS should facilitate an operator's ability to make quick and high-quality decisions and take fast actions. Boyd considered orientation as the most important component. Orientation shapes the way a person observes, the way a person decides, and the way a person acts. Some people prefer to be hands-on rather than work behind a computer screen. Team players may want to collaborate on possible decisions or validate a decision. Some operators may have a personality that make quick decisions come natural. Some operators may have a personality that makes decisions come slower, as they prefer to gather as much information as possible in order to increase their confidence in the final decision. Of these orient factors, training is perhaps the most important method to improve the orientation process. This would include not just basic information, but also training on various problem-solving methods. Boyd intuitively knew this long before he formalized his OODA ideas. Boyd focused on classroom training while as an instructor at Nellis 20 years earlier. It is hard to really do justice to explain in 10 minutes what Boyd could spend 10-some hours explaining after 10 or so years of research. My impression was that these orient factors can be summed up by one's ability to adapt to chaos and one's aggressiveness in resolving the chaos to return back to order. Boyd asserted that in battle, one wanted to generate confusion and disorder in the enemy's mind. The enemy's action will also generate chaos, confusion, and disorder. The aggressive pilot will limit the impact of the enemy's actions by quickly countering and staying on offense. Maybe going through some OODA examples will help. Recall from part 2 of this series that Boyd wanted to understand why the F-86 had performed so well against the more maneuverable MiG-15. One factor Boyd identified was visibility. The bubble canopy gave the pilots the edge in seeing the enemy, which gave them the advantage in the observe part of OODA. In terms of automation, the bubble canopy was equated to high-performance HMI graphics. The other factor was the ability to change directions faster. The hydraulic-assisted controls gave the pilots the edge in executing countermaneuvers, which gave them the advantage in the act part of OODA. In terms of automation, the hydraulic-assisted controls was equated to fully sequenced equipment. A fighter pilot runs through the OODA loop over and over in air combat. The pilot observes the enemy plane moving to attack and looks over the environment. Based on the observation, the pilot will orientate. They will decide on a counter move out of Boyd's aerial attack study and then implement. But before the counter move is finished, the pilot will observe again. They will look to see if the enemy plane has reacted to their counter move, and if so, they will implement another counter move. To win in air combat, Boyd asserts the pilot must act in a faster tempo than that of the opponent. If successful, the enemy plane will never get an opportunity to fire, and, over time, will be forced on the defensive. Victory comes when the opponent either gets frustrated and makes a mistake, or starts to panic because he or she can no longer execute counter moves fast enough. In Korea, the F-86 bubble canopy and hydraulic flight controls allowed American pilots to cycle through the OODA loop faster than the MiG pilots. In a dogfight, the F-86 pilot's mind gained order and control with each OODA cycle, while the MiG-15 pilot's mind gained chaos with each OODA cycle, ultimately leading to mental surrender. In the case of air combat, the fighter pilot wanted to mentally break down the enemy pilot's will to continue to resist. Can an operator mentally break down the equipment that they are responsible for? They can't. So OODA should be focused on managing the operator's frustration. Let's look at a safety example of OODA. On the slide, we have dryer dust discharging into a cyclone bin, funneling into a rotary lock and conveyor. The bin is constantly bridging over and requiring manual cleanout. The cause could be process control over moisture. The cause could be poor feed quality. The cause could be the design of the product bin or the speed of the rotary lock. Regardless of the cause, the system is waging war against the operator. This war is being fought in the mind of the operator. Fatigue, frustration. There may have been complaints about the system that were not addressed, which multiplied the frustration. The cleanout procedure could involve extensive lockout-tagout and production downtime. All of this can break down the thought process of the operator and cause them to take shortcuts, like not using proper tools or maybe even bypassing lockout-tagout. The operator takes a shortcut and cleans out the bin with the rotary lock still running and gets injured. The operator is found to have not followed the rules and is disciplined. Boyd would say that the dryer system got into the mind of the operator and defeated the operator's will to stay in the safety fight. One of Boyd's favorite quotes is, "Machines don't fight wars. Train doesn't fight war. Humans fight wars." You must get into the minds of humans. That's where the battles are won. Behavioral-based safety programs follow this. These programs focus on positive reinforcement. The goal is to keep the workforce encouraged and engaged in their battle to be safe. The positive reinforcement prevents frustration and fatigue, two factors that can lead to unsafe shortcuts. If the equipment went down due to bridging over, was the operator rewarded by being praised for following procedures during cleanout? Or does management not get involved until after an injury? The ability for an operator to comply with safety rules or properly control a process is directly related to his or her mental state. The operator must stay in the fight mentally. This means avoiding tunnel vision. This means avoiding rash emotional decisions. This means problem solving, not problem management. Boyd considered the invasion of France in 1940 as a perfect example of OODA in battle. The German army, under General Heinz Guderian, the father of Blitzkrieg, moved so fast to the English Channel that the French army could not countermove fast enough. Eventually, the French political leaders got discouraged and surrendered. The French army was numerically superior to the German army. German General Manstein wrote in his memoirs that there was nothing in the invasion battle plan that anticipated a German victory over France. Yet, the French army was defeated. The French army was not defeated in battle, though. The leaders of the French army were mentally defeated. The French political leaders, like Prime Minister Renaud, lost their will to continue to fight and surrendered. Since the operator can't break down the mental processes of the DCS, think about how the DCS can attack the mental processes of the operator. One example is when the DCS lies to the operator. Let's look at a common situation of a valve stuck open, but its indication showed closed. How well is this failure situation processed through the OODA cycle? Quick OODA? Automation triggers a reaction and sends a message to the query display to inform the operator. At 3 Mile Island, backup pumps automatically started to correct the cooling water problem, but were rendered useless due to closed manual valves. Automation did not anticipate this problem, so no quick OODA. Automated systems should be fully automated to avoid operators from having to slow down OODA in a crisis to throw hand valves. Medium OODA. An audible alarm is triggered to alert the operator that action is needed to investigate an I/O failure. For 3 Mile Island, there were other I/O points that could have alarmed to help identify the loss of cooling water, but alarms were not configured. HAZOP did not anticipate this problem, so no medium OODA. Or slow OODA. Operator notices the upset condition and investigates. Only then does the operator find the mechanical valve had failed open, which was masked by a closed indication light. The control panels had conflicting information that confused the operators. Ultimately, the problem was caught by the next shift of operators who had fresh minds. The OODA loop can be applied to commercial airline pilots. In 1972, Eastern Airlines Flight 401 crashed into the Florida Everglades. Maybe I should begin with, who has seen the movie The Ghost of Flight 401? This incident became a Hollywood movie starring Ernest Borgnine. In any case, the pilots were so focused on a broken landing gear down confirmation light that they lost track of the external environment. Their OODA loop stopped while they were trying to figure out if it was a real problem or an instrumentation problem, i.e. the computer lying to them. The pilots stopped observing. They had tunnel vision. Ask yourselves, has an operator ever had tunnel vision? Have you ever had tunnel vision? Sometimes the best help a supervisor can give on a job is to observe the environment and look for signs of tunnel vision. Sometimes the worst help a supervisor can give is to roll up sleeves and pitch in. An operator can get so preoccupied with the first couple of alarms in an alarm flood situation that they stop the observe process while they try to resolve those first couple of alarms. A stalled OODA can cause the operator to overlook additional alarms that may be more important. Certainly, observing the altitude of a plane is more important than a landing gear down confirmation light. In 1991, SAS Flight 751 loses both engines and lands in a forest. New automation overrode the pilot's engine control settings. The new automation never considered the situation of ice going into the engines. Worst of all, this new automation was not communicated to the pilots. The pilot took appropriate action to prevent the engine failure, but the automation counteracted it. This situation caused confusion in the pilots' minds. They did what they were supposed to do, yet it wasn't working. The gauges may have shown increased thrust from the automation, but this would conflict with what the pilots expected to see. There were no manuals or SOPs to inform the pilots of the auto thrust automation. The engines failed quickly and the plane went down. Ask yourselves, has automation ever been added without telling the operator? As automation gets more and more complex, the operators will need to know it as well as the programmers and process engineers. Aircraft makers have two unique approaches to automation. Boeing provides information to pilots and lets them make the decisions. This represents probably most of the automation installed with the first modern DCS systems. This would have helped with the SAS Flight 751, as the engine controls would not have changed without pilot input. But it would have hurt with the Ghost of 401 flight, where automation could have detected and corrected the plane's descent while the pilots were troubleshooting the landing gear light. Airbus wants to have the plane's computers make the decisions. If the plane's computers are not properly programmed, as with the SAS Flight 751, this could be disastrous. As plants go to fully automated production lines, operators need to be automation experts and not just button pushers. I believe Boyd would envision a future that looks more like Airbus than Boeing. In terms of the OODA loop, computer decisions bypass the pilot so the OODA loop can happen faster. However, at some point, the pilot or operator needs to be alerted of the action. This is a good application for the query display. Airbus is moving operator error from making mistakes or missing something into a failure to fully vet the automation. A Top Gun trained operator would be the best choice to vet all new automation code. Here are some other ideas to improve OODA. The DCS should have the following: gate alarms by operator, not by control room. Any alarm just for one operator is a nuisance for all of the others in the control room. Full use of the query display. This facilitates the air traffic controller transition for operators. This has been advocated before, but it is improved OODA performance that is the real driver for it. Eliminate reading sheets. Manually writing numbers onto a reading sheet slows down OODA. Automation should be installed to react to any bad values, thus making reading sheets obsolete. Electronic log sheets for operator notes. Searchable and shareable notes, rather than paper logbooks, speed up OODA by quickly allowing new information to enter the Orient section of OODA to better inform the coming decision. SOPs launched by graphics. Storing operator SOPs in some IT database or large binder slows down OODA. A single push button from a high-performance HMI graphic is better. Like with electronic log sheets, quick access to information speeds up the Orient section of OODA. Operators should have the authority to make changes as necessary to all SOPs to ensure that they are accurate. Better synergy between DCS and lockout-tagout. While it is popular to eliminate P&ID style graphics based on high-performance HMI theory, there is value under certain conditions. If the operator has the ability to modify these P&ID style graphics, they can be kept up to date by the operators themselves. Maintaining accurate P&IDs can be a challenge. The red line process for updating P&ID drawings is a struggle even for engineers. For operators working rotating shifts, it is worse if not impossible. OODA training should be part of any Top Gun type classroom training for operators. A Top Gun operator should be on the lookout for situations where the operators are OODA challenged, as well as being on incident investigation teams to ensure that OODA factors are part of the analysis. Boyd's OODA loop provided a common thread to tie his pilot training and his EM theory together and explain how they improved pilot performance. OODA can help improve operator performance as well. General Patton used OODA to defeat his enemies, much like General Guderian. General Bradley was a different type of general, but still used OODA. Bradley and Patton observed the same information, but each had a different Orient section, which resulted in different decisions. Truth is, we all use OODA in our daily lives. These generals do, I do, and all of you watching this video do. Boyd's OODA loop provides a common thread to tie in alarm management, high-performance HMI, and full use of state-based automation for all equipment, and explain how they improve operator performance. The 21st century manufacturing plant must incorporate OODA not just into process automation and operator training, but operations management and engineers as well. A DCS is only as good as its ability to minimize chaos, which ultimately keeps the operator's mind in the fight. This concludes part 3 of the Boyd on Automation series. In part 4, we will learn about Boyd the Reformer and Boyd the Strategist, and how his ideas can be applied to process automation, and in particular DCS selection and obsolete I/O strategy. I'm John Hauge. I hope you enjoyed this mixture of process automation and military history, two passions of mine. I thank you for your interest and your time, and I hope you will tune in for the next in this series.